Hi guys, welcome to the lesson of partial differential equation. So in this class, we are going to discuss the method of eigenfunction expansion for wave equation. We already discussed for the heat equation, and the method is almost similar. Just the difference is that we have second derivative of u with respect to t in this case, and in that particular case for the heat equation, we only had ut, right? So now the boundary conditions are given, Newman boundary conditions, and we know that for applying the eigenfunction expansion, we should have the boundary condition, the homogeneous boundary conditions, right? So if we don't have the homogeneous boundary conditions in the equation, then we have to transform the equation by splitting, that we already learned in the previous lesson, right? So now the idea is that the initial conditions are given, that is ux comma 0 is equals to cosine square pi x, and the initial velocity, that is ut x comma 0 is equals to 2 cosine 2 pi x. And now the method begins with the uh, assumption that the function of xt is given here as cosine 2 pi x and cosine 2 pi t, and the eigenfunction for this particular case will be uh, x and cosine n pi x. All right, we are already familiar with this, that how we can get this eigenfunction by applying the conditions on the equation that we have already separated by using the separation of variable method. And then now we know that for this case, a wave equation, we have double derivative of time, double derivative of u with respect to time. Therefore, we have a n double prime plus n squared pi squared a n is equals to the integral, that is the Fourier integral at the function of xt times the eigenfunction, right, with respect to dx. So we have to integrate this function from limits 0 to 1 that is given here. L, we can see that x is between 0 and 1 by the boundary conditions. Therefore, we will integrate this function from 0 to 1, and this cosine 2 pi t is can be treated as constant. That's why we can move it outside the integral here. And then we know that cosine 2 pi x and cosine n pi x will only give the value when n is equals to 2. Otherwise, it's 0, right? So for n is equals to 2, the value will be 1 over 2. And this 2 will be cancelled with this 2. Therefore, we'll get a2 double prime plus 4 pi squared a2 is equal to cosine 2 pi t, right? Here too, because we already said that we have the value only at n is equals to 2, and for all other n, it will be, the integral will be 0, right? So we can write the equations for all other n's in this manner. Sorry, it's an double prime n squared pi squared a n is equals to 0, right? So for all other n's, it is 0. So now for a naught double prime, it will be equals to twice the integral of cosine 2 pi x and cosine 2 pi t dx, because we know that for a naught double prime, we are going to integrate this eigen function only, right? Here, sorry, not eigen function, this function of x comma t, right? So cosine 2 pi t is again constant, therefore we move it outside, and the value of this integral is 0, because sine 2 pi is 0, sine 0 is 0, therefore a naught double prime is 0, right? Now we will find the initial conditions. So for initial conditions, u of x comma 0 is equals to cosine squared and pi x, right? And we need two initial conditions because it's a second derivative here. Here it is the second derivative, therefore we need two initial conditions. So the first one we'll get from the initial, that is displacement, and the second one we will get from the initial velocity, right? So a naught of 0 is equals to 0 to 1 times cosine squared pi x. Here by mistake I write 2. This is not to here, right? So this is only for integral from 0 to 1 to the this function, right? So for a naught we are not going to use 2 because in the Fourier cosine expansion we know that it's 1 over 2 times a naught. Therefore we are not going to use 2 here, right? So now it's a naught double prime is equals to 0, and now for the initial conditions here, a naught 0 is equals to 0 to 1 cosine squared pi x. That will be equals to x over 2 from 0 to 1. That will be 1 over 2. So a naught of 0 is equals to 1 over 2. And for a2 of 0, we have 2 over 1 times the integral cosine squared pi x times cosine 2 pi x dx, right? So we'll solve this integrals to find a2. And here a2 of 0 is equals to 2 over 1 times the integral of this function, right? So in general, if you want to find an for this particular integral, what we have to do is from 0 to 1, we have to integrate cosine squared pi x with cosine n pi x. But again, you know that we will get the value only when n is equals to 2 here, right? Because now let me construct the solution for this. This is cosine squared pi x means this is 1 plus cosine 2 pi x over 2, right? And cosine n pi x. So we can write in this way cosine n pi x plus will be cosine n pi x plus cosine 2 pi x cosine n pi x, right? Over 2. Integral from 0 to 1. This integral is from 0 to 1 twice. And again, for this cosine n pi x, when we integrate this, we will get sine n pi x, and sine n pi x is 0 from 0 to 1. Therefore, this will be 0. And for this part, we will only get the solution for n is equals to 2, right? So we already worked here for n is equals to 2. Therefore, no need to find an because an is 0 other than for n other than 2n. So we can write here an is equals to 0 for all and not equals to 2. All right, so this is the value of a2 of 0 to integrate this function, and then we will get again 1 over 2. So a2 of 0 is 1 over 2. Now we will find a naught prime. So ut of x comma 0 is given as cosine 2 pi x. Let me check again. What's the value here? It's 2 cosine 2 pi x. Here, this is the value for the initial velocity. So it's 2 cosine 2 pi x. So we will integrate this 2 cosine 2 pi x. This will be 0. So a naught prime of 0 is 0. Then a2 prime of 0, 2 cosine 2 pi x times cosine 2 pi x. Again, we will get the solution as 2, right? So a2 prime of 0 is equals to 2. Now we will use the equation, solving equation 1 with h and static. It means that these are the initial conditions. This is the equation 1. Here it is written. This is a second order non-homogeneous linear differential equation, so we can solve it easily. These are the initial conditions. We will solve the equation. Here we will get the value of a2. Then we'll apply the initial conditions. We will get the constants by using initial conditions. Here, this is A2 prime. So again, applying the condition, we get B2 here. A2 is here. We will plug these values in this equation. All right. So we will get the particular solution for A2. Here is the particular solution for A2 in terms of T. All right, now we are going to solve equation 2, that is for A naught with the initial conditions of A naught. All right, so A naught will be equals to, this is second order homogeneous differential equation. So we can integrate twice to get the result for general result for this in differential equation. So it's A naught T plus B naught. We will apply these initial conditions to find A naught and B naught. Therefore, the value of A naught and B naught is equals to half. Yes, A naught of 0 is equals to half, therefore B naught is equals to half, right? Then we will apply A naught prime 0 for this capital A naught. So we will get A naught of T is equals to 1 over 2 because this A naught is 0, right? So A naught will be equals to 0 times T plus 1 over 2, which gives the result, this one. Now we know that our journal's particular solution can be given by this equation. We calculated A naught, we calculated AN. We just need to plug these values. Therefore, we have A naught as 1 over 2 plus A2 is this function and times the eigen function, that is cosine 2 pi x. So this is the idea to solve the equation using the method of eigenfunction expansion. So we use cosine expansion because Newman conditions were given. Now we'll take a problem on sine expansion. This problem we will use sine expansion because of the Dirichlet boundary conditions. We will have the eigenvalue in terms of sine, function of sine, right? So this will be the eigenvalue. In the previous case, the eigenvalue was cosine and pi x. Here we write somewhere xn, yes, here, this, right? Because of Newman conditions. Now there are Dirichlet conditions. That's why we are going to use this eigen function that we know we will get if you solve the equation for the boundary conditions. And again, the boundary conditions are homogeneous, so we can use the method of eigenfunction expansion. The initial conditions are given. One of the conditions is 0, therefore the problem is pretty simpler. Now the function of xt is x sine t. The eigenfunction is sine n pi x. Therefore, we will use a n double prime plus n squared pi squared a n. No a naught because this is sine expansion, right? So a naught is only for cosine expansion because we know that in sine expansion we only have summation a n of t times sine n pi x, right? Where n is equals to 0 to infinity. Now we will solve this a n double prime, this equation. We will solve the integral here, and finally we will get the result. A n double prime plus n squared pi squared a n is equals to twice negative 1 to the power n plus 1 sine t over n pi. All right, so now you should be familiar with these Fourier series problems to make the problem easier. All right, so this is a second order or ordinary differential equation, non-homogeneous. Therefore, we will have a particular solution and a homogeneous solution, and we will use the superposition principle to get the particular solution for this ordinary differential equation. Therefore, homogeneous equation we can find by using a double prime is equals to negative n squared pi squared a n. From here, we will have r squared is equals to negative n squared pi squared, which means r is equals to plus minus n pi iota, right? So we have complex roots. All right, Therefore, the solution will be in terms of sine and cosine, right? For a and p, we will use the operators d method. Here, 1 over d squared plus n squared pi squared times this function. All right. So here sine t, it means that the coefficient of angle is 1, right? Because sine t, that means it's sine 1t. So we will plug negative 1 in place of d. That will make it negative 1 squared, right? So now it will be 1 over n squared pi squared minus 1 times this function, right? So here is a particular solution for this ordinary differential equation. Now we need the initial conditions to find the particular solution to the problem by finding the coefficients, constants of integration. So an of 0 is equals to 2 over 1 times the integral with sine n pi x dx. Therefore, we are going to solve this integral. All right, so by solving this integral, we are going to get the value of an 0, that is the initial condition for the problem, and an prime 0 will be equals to 0 because the initial velocity is given ut x comma 0 is equals to 0, right? So we will only have an of 0 here, that is we solve the integral, we apply the limits, and then we get this function. All right, so and then an prime of 0 is 0 because ut x comma 0 is given as 0. So we have two conditions now, that is an of 0 is equals to 8 over n cube pi cube, and an prime of 0 is equals to 0. Now we can find the constants an and bn. So we will apply the conditions to the equation. Here, this is an prime. We will plug the values. T is equals to 0. We will get bn, and then we will get this an respectively, right? This is bn, and here this is an equals to this function. Now we can plug in the equation to find the general solution. So a and t now is equals to this whole function. So the solution of this equation is an of t times the eigenfunction, that is sine n pi x. Therefore, this will be the particular solution for this problem with the given boundary conditions and initial conditions, right? So this is the method of eigenfunction expansion, very useful method when you have a non-homogeneous wave equation with time-dependent sources and homogeneous boundary conditions with some initial conditions. Therefore, we can use this method to make the problem simpler, right? So hope you guys will learn from this lesson. Goodbye till the next lesson. That's all for the time being.